Welcome to ME 286, Theory of Plasticity. My name is David Steigmann, Professor David Steigmann in the Mechanical Engineering Department. This course is dedicated to the modeling of plasticity in metallic materials of principal interest in engineering. And it presumes that you have some acquaintance, at least with introductory continuum mechanics, at the level of ME 185 or 287 in this department, or the equivalent course in the civil engineering department. A good background reference for people who want to refresh their knowledge in this area is the small book by Chadwick, Continuum Mechanics, Concise Theory and Problems, and that is published by Dover and is very inexpensive. I would recommend that highly for people who want to review continuum mechanics. Okay, well, let's begin with a short lecture today, the first lecture, in which we describe the basic phenomenology of plasticity, discuss a little bit of history, and then begin a quick review of basic continuum mechanics that we will build upon for the rest of the course. So the basic idea, plasticity can be understood from a simple tension test, let's say on a thin wire or a thin metallic bar. Suppose the wire has length L sub 0. When it's unloaded, we apply no force on the bar. Here, when I say force, I mean an axial force. Suppose this bar is unloaded and has length L0. And then we apply a load, a force, say a tensile force, and the bar extends to a length, say L. And we can plot the data in this way. We can plot the stress, the Cauchy stress, which is the force divided by the cross-sectional area, provided that the Cauchy stress is uniformly distributed over the cross-section. Otherwise, of course, the force is the integral of the Cauchy stress over the cross-sectional area. And here A is the current cross-sectional area associated with the current state of the wire or the bar. What we observe when we apply the force or the stress is that the wire extends with a stiffness, say, call it E, which is Young's modulus. And that extension proceeds in a more or less linear manner if we plot the stress versus the natural logarithm of the stretch. The stretch is just the ratio of the current length of the bar to the initial length. Metallurgists find it informative to plot the stress against the natural log of the stretch. That's called the logarithmic strain. And the reason for that is that in terms of these variables, t and natural log lambda, the experimental curves typically exhibit a tension compression symmetry, so that if you were to reflect this on the two axes, you would find essentially the same response in compression. And so that's a common way of representing the test data. So the response proceeds linearly with a stiffness equal to E, the Young's modulus, up until a certain point we call T sub y the yield stress, at which the slope of this curve begins to diminish very rapidly. And the point at which this happens can be detected by unloading the bar and seeing at which stage does the unloading curve begin to differ in a detectable way from the loading curve. When that begins to happen, we call that the yield condition of the bar. And typically the unloading then will proceed along this a parallel line with this roughly the same slope, the Young's modulus. With continued loading, the stress will increase like so, but its increase is limited by this greatly diminished slope. Let's suppose we reach another point here on this loading diagram. This so-called yield stress will evolve It can be different from the initial value of the yield stress. If we now unload from this point here, shown by my cursor, then we again unload along a line that is roughly parallel to the initial loading and unloading curves, again with the same, roughly the same slope, E, the Young's modulus. And we can unload, say, to zero force or zero stress in the case of uniform stress. The value of natural log lambda, we'll call it natural log lambda sub p, where lambda sub p is the stretch in this unloaded state, that is the length of the unloaded state, I'll call L sub I. The subscript I is intended to indicate an intermediate configuration. So L sub I divided by the initial length we'll call the plastic stretch. And that's associated with zero value of the force, or in this case, zero value of the stress. When we load up again from this point, in tension, let's say, we again follow the same curve, approximately the same curve, until we very nearly rejoin the initial loading curve, at which point the slope again diminishes greatly. So we have yielded the material again. And we can continue this process. We can load up to another point here, unload again, and the same phenomenology is observed. Unloading approximately linearly at a slope equal to the Young's modulus, reloading, and so on. And a similar response in compression, essentially the same response in compression. If the material, if this greatly diminished slope is not exactly zero, if it's slightly positive, we refer to that as strain hardening. The material continues to sustain increasing load, but at a much diminished stiffness. A useful idealization for many materials is perfect plasticity, in which this, after yielding, the stress saturates to a fixed value, which is the initial yield stress. That's associated with this dashed horizontal line. And that is a very useful idealization in the analysis and formulation and analysis of problems. Okay, so we've introduced these two notions of stretch, lambda, the overall stretch, lambda p. And here, to make the equality, we need another stretch, L over this length over this length. That's we call the elastic stretch. And the reason is, loading from zero up to the current value of yield stress is achieved, that the value of stress is achieved by multiplying the Young's modulus times this difference, natural log lambda minus natural log lambda p. So you can think of this as an elastic strain. The elastic strain times the elastic modulus furnishes the current value of the stress. Okay, so again, the plastic stretch is the overall stretch when the stress is zero in the uniform case, or in other words, lambda sub elastic is equal to 1 when the stress is zero. So the reason I'm discussing a uniform state is because then the stress and the stretch can be inferred from boundary data. Right? Otherwise, in the non-uniform state, all we have is that the integral of stress over the cross-section is the force. And lambda is really then a function, typically a function defined pointwise in the material. In the event of a uniform state, we can correlate that with boundary data. Okay, so from this diagram, the stress, let's say this value here, is the Young's modulus times this difference, natural log lambda minus natural log lambda p, which of course is the natural log of the ratio, which is just natural log lambda sub e elastic. So this is the natural log lambda e is the elastic strain. We can recount some of the observations we've made so far. The elastic properties of the material, in this case, simply the Young's modulus, is quite insensitive to the value of lambda p. For example, here lambda p is 1, and here's the Young's modulus. Here it's a different value, essentially the same Young's modulus, and so on. A different value of lambda p here, and the same Young's modulus. So the elastic properties in the simple tension test are insensitive to lambda p. Of course, the only elastic property we have at the moment is the Young's modulus. However, this general notion that the elastic properties of the material are insensitive to plastic deformation is confirmed in famous experiments conducted by G.I. Taylor many years ago, 1931, in this very influential paper called The Plastic Distortion of Metals, published in the Royal Society. We will come back to this. Essentially, what a crystal lattice, the structure of the crystal lattice, is not significantly disturbed by plastic deformation. And therefore, the elastic properties, which are inherited from the structure of the crystal lattice, are also preserved, insensitive to plastic deformation. Something else we observe, although it's not indicated in the figure, is that the yield stress, T sub y, even if it changes, even if it evolves, is very much smaller than the value of the Young's modulus. And these, of course, have the same physical units, so their ratio is dimensionless, and that ratio is much less than 1 in magnitude. So the absolute value of stress, be it tensile or compressive, divided by Young's modulus, that's of course bounded above by the current value of the yield stress divided by Young's modulus. That will be very much smaller than 1. So if we look at this simple equation, the absolute value of the ratio T over E, that's just natural log lambda sub E, is much less than 1, which means lambda sub E must be close to 1. Not exactly 1, of course. If it were exactly 1, there would be no stress, but close to 1. So this suggests that we Taylor expand this elastic strain with respect to the value 1. So Taylor expand this about lambda E equal 1. And so this is the Taylor expansion through linear order. And this just delivers lambda E minus 1. This notation small o here is a well-established notation. It's called a Landau symbol. It simply gathers together all the terms that are smaller than the linear term in the limit when the linear term goes to 0. So for example, small o lambda E minus 1 encapsulates the nonlinear term lambda E minus 1 squared, or lambda E minus 1 to any power which is greater than 1. Okay? Any term that goes to 0 faster than lambda E minus 1. So for lambda E close to 1, we have an approximate stress elastic strain relationship given here, where we define this to be according to our definition of epsilon here, this is the elastic strain, lambda E minus 1. So again, the stress vanishes when lambda E equals 1. And we notice, of course, in this simple uniaxial experiment, that the stress can then be written as the derivative of an energy, the derivative of W with respect to its argument, where W is just a half Young's modulus times the square of the elastic stretch, just like a linear spring. Something else we can observe from the diagram here is that as long as the stress does not exceed the current value of the yield stress, or as long as the stress is below the current value of the yield stress in magnitude, this lambda p does not change. Okay? It's only when you yield the material that the plastic stretch can evolve. Okay? So that's our third major observation. Lambda p does not change as long as the absolute stress is less than the current value of the yield stress, that begs the question, how does lambda sub p evolve when we reach the current value of the yield stress? So this is one of the main problems in the theory of plasticity, how to decide how lambda p should change when you yield the material. That's the result of that analysis we would call the flow rule, which prescribes the manner in which the plastic deformation evolves. A very brief history. I'm certainly not expert on the history. There's an outstanding book by Professor James Bell from some decades ago on the experimental foundations of solid mechanics, and I've indicated that in one of the announcements on B courses. And if you're interested in the history going back several centuries and up to and including the late 20th century, you should consult that very fine encyclopedia article by Bell. Plasticity has a very long history. I think it begins essentially with Coulomb, who was interested in the yielding of soils, plasticity of soils, in the context of geomechanics. Much later, there was a significant development in which Maxwell, the same Maxwell that you know from electromagnetism, wrote a letter to someone named Thomson, in which he develops the basic idea that was later to become known as the von Mises yield criterion, to decide at what state of stress does a material yield. In the late 1800s, Tresca, whose name you're familiar with, I'm sure, conducted very important extrusion experiments on materials, establishing an experimental foundation for plasticity. Later, Saint Venant, the same famous elastician that you're familiar with in the context of torsion theory, elastic torsion theory, he developed a two-dimensional theory of plastic flow associated with what we call today the rigid plastic theory, in which the elastic deformation is neglected. If the overall deformation is large, and as we've indicated previously, the elastic strain is quite small, that is lambda sub e is close to 1, then it's a useful idealization is to neglect the elastic deformation altogether. And that's the subject of the so-called rigid plastic theory. Later in the 1800s, Levy extended Saint Venant's work to 3 dimensions. In the early 20th century, von Mises, whose name you're of course very familiar with, established his famous three-dimensional yield criterion, which stipulates the conditions of stress that are associated with the onset of yielding. And we will discuss that in at great length. It's a very important development in plasticity theory. A bit later in the early 20th century, Prandtl, whose name you're familiar with, in the context of boundary layer theory and fluid dynamics, developed a very elegant two-dimensional theory, a plane strain theory called slip line theory, which we will discuss at length in this course, for which there's a vast literature and a subject that has interesting mathematical features. A little bit later, a woman named Hilda Geiringer discovered the equations that describe the velocity field associated with the so-called slip line theory, thus providing closure for this theory. Somewhat later, von Mises made a study of crystalline deformation. We'll talk a bit about, or we'll talk rather extensively actually about crystal plasticity. In the middle of the 20th century, Rodney Hill published a famous and very influential book, Mathematical Theory of Plasticity, which was an authoritative treatment of everything that was known up until that time in plasticity. And this remains a very significant and important reference to the present day. With the reinvigoration of continuum mechanics in general in the mid 20th century, in the post-World War II period, in the 1950s and 1960s. This saw the very extensive development of what we would call the modern theory of plasticity valid for finite deformations, and including many beautiful developments coming from the differential geometry and tensor analysis, rather advanced ideas that are similar in many ways to the methods used by Einstein in developing the theory of gravitation, relativity theory, in terms of so-called non-Euclidean spaces. And we'll find that plasticity theory affords a very interesting setting in which to exercise these developments in differential geometry. And so we will devote some significant space to the differential geometric aspects of the subject in this course, in particular with regard to the description of dislocations, which are the essential mechanism through which, by which plasticity occurs in metals. And to this day, the subject undergoes very active development. There's an enormous activity in terms of numerical analysis. In this course, we'll discuss mainly theory, although we may get to some of my own very modest efforts with collaborators in the numerical analysis of plasticity later in the course. But the emphasis here is on developing theory and solving problems. Okay, so by the way, I would say in this period of time, since the 1960s to perhaps around the early 21st century, there are many schools of thought, often in conflict with each other. People would argue relentlessly about which formulation is right, and so there's a lot of controversy in this subject. I would say that the subject has reached a state of maturity at this point where certain controversies have been resolved, and there is a broad agreement on most of the fundamental aspects of the subject, although controversies continue to the present day. The reason for this is that plasticity theory is quite a difficult subject in terms of quantitative analysis. That is to say, to devise a theory that's capable of making quantitative predictions about metal plasticity is a very challenging task, and this difficulty has given rise to a number of different schools of thought in the subject, as well as attendant controversies. Okay, but enough is well established now that a course can be justified concerned with the aspects of broad agreement in the subject. Okay, so let's have a look at a very simplified view of the basic phenomenology at the microscale, at the scale of a crystal lattice. So here's a schematic diagram of a crystalline lattice, for example, a cubic crystal, like iron, for example, a single crystal. And here you have a lattice points. The basic fundamental lattice is one of these squares or cubes. And at the intersecting points of these lines here, you have an atom in the lattice. And the basic mechanism of plasticity, for example, if you prescribe shear displacements or shear stresses, as indicated here, the basic mechanism is the sliding of one plane of atoms over the next plane, like so. So, for example, if you have a unit depth of crystal, then this sliding of one plane of plane of atoms over the other produces, on the macro scale, a shear deformation. So these steps have a length equal to one lattice spacing, which is a submicroscopic length scale. So on the macro scale, you would perceive this as a shear deformation. So we would call a macroscopic plastic shear is due to relative sliding along crystallographic planes. That sliding is a frictional mechanism and an inherently dissipative mechanism in which energy is dissipated and much of it is converted into heat, for example. In this course, we'll discuss mostly the purely mechanical theory, although later, near the end of the course, we'll revisit the main aspects of the subjects from a thermodynamical perspective. So the question arises, how is this relative sliding achieved? It's produced essentially by the motion of dislocations. And this brings us to a nice diagram in a recent book by Gerten and associates, published about 10 years ago. Let me turn to the next page quickly and discuss an excerpt from that book. So here we have a crystal lattice which is disturbed by a plane of inserted atoms here, which we can think of as a defect in the crystal. And this inserted plane has the effect of disturbing the arrangement of the lattice locally. We will call this column of atoms here, this third column, viewed edge on, so it's really a plane of atoms. We will call this an edge dislocation. And this dislocation is the basic mechanism by which plastic slip occurs as follows. So for example, imagine shearing the crystal as shown here, and let's concentrate on this line of atoms containing this terminal point of this edge dislocation. So imagine shearing the crystal, apply a shear stress or a shear deformation macroscopically. This will cause a stretching, say for example, of this bond labeled AB right here. This bond, if you can see it with my cursor, will become stretched to the breaking point. That bond will break. Meanwhile, this atom is in closer proximity to this one as this shear displacement occurs. And a bond is formed then between these two atoms in lieu of this bond which is broken. So we now have a bond between those two atoms, whereas the previous bond is broken. So the effect is to transfer the edge dislocation from the third column of atoms essentially to the fourth column. The atoms themselves have not undergone a significant displacement, but the set of atoms associated with the edge dislocation has transferred to the right in this diagram, as you see here. So let's imagine then, this bond breaking and reformation of a bond with a different atom is the basic mechanism by which a dislocation can move. So imagine again a perfect lattice here with no defects. We shear the lattice. Let's suppose for the moment that this shear induces a non-uniformity in the local deformation of the lattice. We'll come back to that point in a moment. The shearing of the lattice will stretch this bond, let's say here, stretch it to the breaking point. The bond breaks. This adjacent bond is then stretched as well. It breaks. Meanwhile, this atom is in closer proximity to this one and forms a bond. So now what we've done in effect is to introduce an edge dislocation into the crystal lattice through this bond breaking mechanism. Here's this edge dislocation. We continue the shear displacement. This process repeats. A bond is broken, and a bond is broken, and a new bond is formed, like so. And the effect is the dislocation, which was now associated with the second column of atoms, is now associated with the third column. The dislocation has traveled one lattice spacing to the right. And this process continues, as indicated here, until the dislocation continues to move one lattice spacing to the right, until, for example, if this is the entire lattice, until it's effectively been expelled from the lattice. But the net effect is that this upper layer of atoms, 2 layers of atoms, has displaced to the right relative to the lower layer. So we have this mechanism of sliding due to the passage of an edge dislocation. You can find a detailed discussion in this book by Gurtin, Fried, and Anand in Cambridge 2010. You might ask, the obvious question here is, well, why doesn't this happen to the entire lattice all at once? After all, we have, the effect of the shear stress or shear displacement is felt simultaneously in the entire lattice. Why not have this sliding mechanism occurring all at once in total without going through the intermediate step of a sequential movement of dislocation? And the basic reason can be understood through an analogy with a carpet or a rug. So for example, suppose you have a carpet sitting on a floor, and you wish to displace the entire carpet to the right by a certain amount. So this is analogous to one layer of atoms sliding over the other layer in the crystal. What we could do is we could grab hold of the rightmost edge of the carpet and simply try to pull the whole thing to the right. If we try to do that, you can imagine that would be a very difficult task because of the friction with the floor. To translate the carpet all at once to the right, all points of the carpet to the right, takes a lot of force, and you probably could not do it by yourself. For a normal sized carpet, you would need your friends to help you. A much easier way to achieve the same objective is to create a bulge at the left end of the carpet, just a bump in the carpet, and simply move the bump, translate the bump from left to right. So you just push along the bump, easily done by one person. And when the bump has emerged from the carpet, the effect is to displace the carpet slightly to the right, just as in the same way that the effect of the passage of a single dislocation has been to displace the upper layer of atoms slightly to the right relative to the lower layer of atoms. So this mechanism requires, as you can imagine, intuitively, far less force or energy to achieve than trying to translate the entire carpet all at once. And this is the reason, essentially, why this plastic slip process happens through the translation of dislocations. It's an energetically favorable process, and it requires minimal energy or force to achieve. Let me now return to the previous slide. In continuum theory, we don't model the discrete dislocations, the discrete atoms and the discrete dislocations associated with them. We model a continuous field of deformation. And in continuum theory, we describe the kinematics of dislocations, essentially, in terms of a non-Euclidean geometry. In continuum mechanics, when we analyze deformation and so on, we are accustomed to working in Euclidean space, the ordinary space of position vectors that we're accustomed to. From our perspective, we can define a Euclidean space, or the conventional space in which we have our experience, as a space of position vectors associated with, say, a single Cartesian coordinate system that can cover the entire space. So for our purposes, we can define a Euclidean space to be a manifold that can be covered by a single Cartesian coordinate system. In the non-Euclidean space, we have no position vectors in general. And in fact, this is the mathematically appropriate way of describing a continuous field of dislocations, and we'll discuss that quite fascinating subject in this course. Okay, we discussed so far the phenomenology associated with single crystals. Most engineering metals, for example, are polycrystalline in nature. That is to say, they consist of many, many microscopic grains within each grain we have a single crystal. And so we have here an aggregate or polycrystalline aggregate of single crystals. In an engineering theory or a continuum theory, we would like to be able to associate this aggregate behavior with the properties of a material point. So macroscopically, we would like to have a theory that represents the aggregate polycrystalline behavior. Typically, these crystal grains are randomly oriented, that is, they have no specific orientation, so they're approximately randomly oriented in practice. So from the macroscopic perspective, they can be treated as approximately isotropic macroscopically. And so the classical theory of plasticity, the isotropic theory, which is the subject of the theories put forth historically that I mentioned previously in the distant past, that theory pertains to isotropic response. That turns out to have great utility in engineering precisely because most engineering materials are polycrystalline with approximately randomly oriented crystal grains. They interact with each other at these grain boundaries. Okay? So we will discuss at great length the isotropic theory for this reason. Okay, we are at the point here of beginning a rapid review of basic continuum mechanics. Again, I'm hoping this is review because a prerequisite for the course is the first course in continuum mechanics. So we'll discuss standard continuum mechanics as conceived by Cauchy and his contemporaries. We start with kinematics, which has nothing specifically to do with Cauchy's perspective, but nevertheless. So we have a body that we perceive in a configuration, let's call it kappa sub t, at the time t. We would call this the present configuration or the current configuration of the material points constituting the body. And we imagine this configuration to be a volume in our Euclidean space of our common experience. And it's constituted with material points P, which have positions. Let's, for example, choose an origin in space. We can describe a material point by giving its position at time t. We can subtract from that position the position of the origin, and the result is a position vector. Okay, this position vector can be viewed as the difference of two positions. So we can associate a vector space with our Euclidean point space, so-called. Okay, so the position of material point P we'll call small x. And the possibility of making this description is associated with the idea that the body is immersed in our Euclidean space at time t. For the purpose of analysis, it's useful to describe the motion relative to some configuration, say fixed configuration that we call a reference configuration, kappa sub r, in which the position of the material point, the same material point P, is given by capital X. The objective then is to describe the mapping of this position into the position at time t. This we would call the deformation chi. So small x is a function chi of capital X and t. One thing we immediately must notice is capital X depends on the manner in which we choose our reference configuration, whereas small x has nothing to do with the reference configuration. So the value of this function is not dependent on a reference configuration, although its argument, capital X, certainly is. Therefore, the function itself, kappa or chi, depends on the choice of reference configuration. So in principle, there should be a subscript kappa r, chi sub kappa r, to indicate this dependence, but that notation would be cumbersome, and so you simply should keep it in mind as we proceed. Again, kappa sub t is the configuration we perceive of the body at time t, a volume in space. Kappa sub r is a reference configuration, which is arbitrary in principle, but subject only to the restriction that to each point of the body, each atom or molecule, if you like, of the body, there corresponds exactly one position in the reference configuration. So the body is in one-to-one correspondence, fixed one-to-one correspondence with the reference configuration. And the same for small x, right? Position in kappa t should be in one-to-one correspondence with the material points in kappa t, so that we could not have, for example, two material points occupying the same position at a given time. So this is the only stipulation that we impose on the reference configuration, although very often in the literature and in most coursework, people find it convenient to take an initial configuration as the reference configuration. So for example, we could take the actual configuration occupied by the material at some initial time t0 and choose that to be our reference configuration, our fixed reference configuration. It's by no means necessary to do that, but it's often very convenient. So as I've mentioned, we assume that to each point of the body, so imagine the body is a kind of abstract manifold, P belongs to the body. So the material point has an identity all of its own, regardless of how we perceive it in physical space at any time. So that the points of the body are in one-to-one correspondence with points in the current configuration, also in one-to-one correspondence with points with positions in the reference configuration, and therefore the reference and current configurations are in one-to-one correspondence with each other. That is, there's a one-to-one correspondence at any given time between small x and capital X. That essentially means that this deformation function is invertible at any given time. So if we fix the time, you can invert this function in principle. This is a physical requirement we will impose. You can invert this function so that if I tell you the location of the material point, small x, at time t, I should be able to identify the position that that material point has in the reference configuration. This is what we mean by this invertibility. Let's suppose further that this function is differentiable, both with respect to capital X and t. For the moment, let's fix the time t and consider the derivative with respect to capital X. Differentiability then simply means, as it does in the conventional notion of a derivative, that for points, say, capital Y and capital X that are close to each other in the reference configuration, in the sense that the distance between them is small, then this difference, chi at y minus chi at x, is approximated by a linear function of capital Y minus capital X. And that linear function, as you know from continuum mechanics, or linear algebra, or calculus, has this form. A tensor, f, we call the deformation gradient, associated with point capital X and time t, operating on the vector difference y minus x, plus a nonlinear part, small r, a vector valued function that depends on capital Y, capital X, and the time t, which is obscured here. This r is interesting only to the effect that its norm, its modulus, is small o of the distance between y and x. Small o, recall, collects all terms that are smaller than the norm of y minus x as y minus x approaches 0. So differentiability simply means that the difference of the function values is approximated by a linear function of the difference of the arguments. Okay. So this we take as our definition of derivative, essentially the so-called Fréchet derivative in this context. And this f is called the deformation gradient, which is a fundamental kinematic variable in continuum mechanics, usually written f equals grad chi to indicate that it's essentially the gradient of chi. So here we have the definition of the deformation gradient. That's fine. Unfortunately, it's not an immediately useful definition. Let's see if we can use the definition to extract something that is more directly useful. To that end, let's imagine drawing a curve in the reference configuration consisting of a fixed set of material points. So it's a fixed curve, C, in the reference configuration. We'll parameterize it by arc length, capital S. So the parametric representation of the curve will be capital X of S. And let's have a point here, x1, which is x evaluated at arc length value S1. x2 is x evaluated at arc length value S2. And for points in between, we simply have x of S. Okay? We can use the definition of the deformation gradient, the differentiability assumption, to write chi at x2 minus chi at x1. So these are these points after deformation, not shown here. Chi at x2 minus chi at x1 is f at x1, multiplying or operating on x2 minus x1, plus a nonlinear part that depends on x2, x1, and the time. Okay. So these would be the deformed positions of these points at time t. However, x2 minus x1, these 2 points on this curve C, these are x at S2 minus x at S1. And if the curve is differentiable itself, that is the parametric representation is differentiable, then this difference can also be approximated by a linear function of S2 minus S1 when S2 is close to S1, or S2 minus S1 is small in magnitude. That linear function is the derivative x prime evaluated at S1 times S2 minus S1 plus small o of S2 minus S1. Again, assuming that the curve is smooth, that is capital X of S is differentiable. So we can substitute that in here, noticing that x2 is chi x at S2, x1 is x at S1. We substitute this expression here from the second line. We get f at x1, x prime S1, then small o, S2 minus S1. That is of the same order of magnitude as r, which is the distance between x2 and S1. Now, let us divide this equation by S2 minus S1. On the left, we have this. On the right, we have this. And then we have small o S2 minus S1 divided by S2 minus S1. If we now take the limit as S2 approaches S1, then this ratio will disappear because the numerator tends to 0 faster than the denominator does as S2 approaches S1. So then this part disappears in the limit. On the left, we simply get the derivative of chi with respect to S evaluated at S1. On the right, we get f evaluated at x1 times x prime evaluated at S1. Again, time is fixed. So here, the understanding in computing this derivative is that chi has been written as a function of capital S by inserting the parametric representation of the initial curve into the deformation function. Well, we can remember this more easily, perhaps, by remembering that the value of chi is simply the current position at time t. We can rewrite this equation as dx equals f d capital X. If we think of multiplying this equation through by d capital S, it's essentially this equation. All we've done, of course, is to is to prove the chain rule. So this is really the chain rule representation of the deformation gradient. And it so happens that this formula, this is an exact formula, is much more useful in applications than the original definition of the deformation gradient. Something to be mindful of in terms of the geometric interpretation, in our reference configuration, to obtain this result we just had, we formed a difference, x2 minus x1. That's the chord along the curve connecting the points S1 and x2. And then we computed the derivative of the parametric representation in this way. As S2 approaches S1, the chord, of course, becomes closer and closer to the tangent. So as S2 approaches S1, you can see immediately the chord becomes becomes tangential to the curve in the limit, so that this derivative is tangential to the curve at the point S1. So we could think of this d capital X, which is that derivative times ds at the point x1, that is also tangential to the curve. After deformation in the current configuration at time t, we have a similar idea. This is the deformed position of this point at S1. This small x2 is the deformed position of this point. We continue to use the parameter s to parameterize the curve, although in this configuration, s no longer measures arc length, because we imagine that in the course of deformation, we have stretched and rotated the curve, maybe compressed the curve in length, so that if S2 minus S1 was measured length in the sense of a tape measure stretched along the curve, conforming to the curve, then S2 minus S1 would no longer be an indication of arc length along the curve. You would still have an arc length along the curve, but it would no longer be the number S2 minus the number S1. Right? You imagine attaching a tape measure with labels S1 and S2. S2 minus S1 then is the physical arc length. The tape measure stretches with the curve, but S2 minus S1 is no longer the length of arc. It's a different number in this configuration. But nevertheless, the same argument here shows that d small x is tangential to the deformed curve at the same material point here. Okay. So we have the idea that these differentials dx are tangential to the curves. Here, of course, the parametric representation of this curve in terms of capital S is obtained simply by inserting the original curve, capital X of S, into the deformation function. Okay, we can imagine, for example, two intersecting material curves, intersecting at the material point P with position capital X in the reference configuration, and position small x in the current configuration, the same material point. Here's one material curve, here's another. They intersect at an angle, they enclose an angle capital theta, for example. This curve has a differential d capital X tangential to this curve at point P. This curve has a d capital Y tangential to this curve at the same point, and so on. Their images here, d small x, d small y, tangential to the images of these material curves in the current configuration of the body. So here in this chain rule representation, of course, f is evaluated at the point x1, or in generically capital X. Right? So we have the same formula here, in which f is evaluated at capital X. In this formula for dy, we have the same f. F is again evaluated at capital X. We can form the scalar product, or the Euclidean dot product of these two vectors, dx and dy, in this way. From the definition of transpose from linear algebra or continuum mechanics, we can rewrite that in this way, d capital X dot f transpose f dy. And then we arrive at a tensor capital C that's called the right Cauchy-Green deformation tensor, an awkward terminology, but one that's widely used. That's simply F transpose F, and this is immediately a symmetric tensor. Its utility lies in the fact that it describes the local state of distortion of the material in the neighborhood of the material point P. For example, if we take the two curves to be the same curve, so collapse this curve onto this one, and therefore this curve onto this one, then dy becomes dx, and we have the squared length of dx. We can compute that from C by taking d capital Y to be d capital X. So we can compute the lengths of material curves in the neighborhood of the material point P, and we can also compute the angle. For example, we can relate this angle capital theta to this angle small theta enclosing these two curves. So this is what we can do that for any pair of material curves passing through material point P. And in this way, we describe the local state of distortion. So this tensor C, derived from the deformation gradient, characterizes the distortion in the infinitesimal neighborhood of the material point P. A measure of distortion that is more commonly used in engineering in any case is the so-called strain. Here we call it Lagrange strain, which has the property of vanishing when the body is undeformed. When the body is undeformed, you have here d small x is simply d capital X when the body is undeformed, so F is the identity. Then C would be the identity, and if we subtract the identity, we have a measure of distortion that vanishes when the material is undeformed, and the factor 1/2 is simply inserted here so that this linearizes, in the case of small displacement gradients. In that case, with the factor 1/2, this will coincide in the limit of small displacement gradient with the classical infinitesimal strain tensor used in linear elasticity, for example. And here, I is the identity, simply that maps any vector to itself. Okay, that's our very brief introduction with some background in the kinematics of continua. Again, I'm hoping sincerely that this is review because we will make frequent use of these ideas without mentioning them. Next time, we'll start with a very simple example in which we use the chain rule to extract a representation of the deformation gradient in terms of Cartesian coordinates. And then we will review the notions of stress, the equations of motion, and so on next time. Thank you very much.